Continuing on with the Chapter 8 assignment. Here we are. Let's get a timer going and a few things. There we go. Okay, continuing on with the Chapter 8 assignment with problem number 24. This is about electronegativity, and you probably don't even need a periodic table to do this because you're supposed to put them in order of increasing. Oops. Go back there, find a pen to write with. Increasing electronegativity. And since you know the smallest electronegativity is here and the largest electronegativity is here with fluorine, you know the general trend. And so bromine is going to have a lower electronegativity, chlorine next, and fluorine highest. So that would be, why didn't I start on A here, I wonder? Okay, let's go back to A. Increasing electronegativity. Remember, the trend is this is the lowest. So we increase in electronegativity as we go up, and we increase in electronegativity as we go across, with fluorine being the highest. So these three elements are in the alkali metal family, and so the smallest electronegativity will be at the bottom of that group. Here we see gallium, boron, and oxygen. And gallium is the lowest here. Oxygen is closest to fluorine, so it's the highest, and boron would be right in the middle. And by the way, do you remember why I have this X here between arsenic and selenium? Well, that's where the electronegativity of hydrogen falls, in case we need to know that at some time. That's where hydrogen belongs in the electronegativity scale. So there is number 24C. And of course, the difference is here that the reason they gave you these three in the problem was they wanted to see if you would recognize that in the alkali metals they increase in the family as we go up, but here, increase as they go up. Here we also increase, but it's sometimes easy for people to get those confused and get them switched around. So bromine is less than chlorine is less than fluorine, and so they're in order of increasing. Sulfur, oxygen, and fluorine. Of course, if fluorine is the highest and sulfur is the closest to this corner of the periodic table, making it lower of the three, and oxygen in the middle. Let's see if we can move on to a new problem here. Number 25. Now, this also is based on electronegativity because we're supposed to simply say which is the most polar of a bunch of pairs that are in the list, like carbon fluorine, silicon fluorine, or germanium fluorine. Well, you notice you could figure that out by deciding which pair is the furthest apart on the periodic table. And in that particular case, circled that in red down here, that's germanium and fluorine are the furthest apart of those three. Phosphorus and chlorine is B. So here's phosphorus and here's chlorine, and so the others must have been closer together. The other, let's see, this is 25B. The other one was sulfur and chlorine. The other thing to look at was sulfur and chlorine. So the phosphorus and chlorine are further apart, so they will be the most polar because they will have the greater electronegativity difference. C was sulfur and fluorine. Sulfur and fluorine had the greatest electronegativity of the pairs presented in C. And D, here we have Ti and Cl. And of the pairs, they must have been the farthest apart. Number 26. Now here we didn't have quite as much, well, there was a lot more variability within the problems, the pairs that were shown, and so it might be really useful, in fact it might be almost necessary, to use the table 8.3. And also, if we're not using the table, we've got to be sure and remember that hydrogen has an electronegativity that lies right here between arsenic and selenium. So, which has the greatest electronegativity difference? Well, tin and hydrogen. Where's tin? There it is. Tin and hydrogen for A. TL and Br. I circled TE over here. Should have circled TL and Br. Silicon and oxygen. And D, oxygen and fluorine. Number 30, indicate the bond polarity. Now, there are several ways of indicating this. Sometimes by using the lowercase delta symbol and a charge indicating a partial positive and partial negative charge. Not enough charge that that the entire electron is transferred, but a little bit of a charge, so the polarity. And of course, the other way of showing that is with an arrow. In the arrow, the arrow is going to point in the direction where there's the greatest electronegativity, indicating the electron is spending a greater amount of time in that area. So if you compare carbon and oxygen, oxygen has the greater electronegativity, so it'll be more attractive. It'll attract that pair of electrons shared in this bond. It'll attract it with more strength, and so the electron will be closer to the oxygen. Now for phosphorus and hydrogen, it's going to be useful to remember that phosphorus is here, hydrogen is kind of here. We might actually just about have to look those numbers up on a periodic table. So let's find a table of electronegativities to look up phosphorus and hydrogen. Let's see, here's hydrogen. Oops, get back to a pen again. I let my pen go away. There's hydrogen, and here's phosphorus. Remember, hydrogen lies right here between arsenic and selenium as far as its electronegativity, but it turns out to be exactly the same as the electronegativity of phosphorus. So there is no partial positive or negative charge. This is very nonpolar. Now if you compare that with hydrogen and chlorine, chlorine is right here with 3, hydrogen 2.1. The chlorine is going to be a lot more electronegative, so we might draw an arrow like this, or we might put the lowercase delta sign indicating a partial positive and partial negative charge. Now, bromine and tellurium. See if I can get some of these to go away. Here's bromine, and where is tellurium hiding? You can see, of course, even if you didn't know the numbers, you'd be able to predict that bromine has a greater electronegativity. So this would be the partial negative and the partial positive charge, and we might draw our arrow this direction. So in number 40, we're looking here at the size of various atoms and ions. And of course, as you remove more and more electrons, because that's what's happening here, is more and more and more electrons are being removed, the size of these ions are going to get smaller and smaller because we have a greater positive charge in the nucleus compared to the negative charge outside, and so the electrons are all going to be more tightly held together. So here we have cesium, rubidium, potassium, and sodium. These are all in the same family. Cesium, rubidium, potassium, sodium. They're all the same charge, isoelectric charges, as we looked at earlier. So here, of course, as we go down this group, what really makes the difference is what valence shell, where the valence shell is. And of course, we're going to get bigger and bigger as we go down. Of course, we've placed them in decreasing size, so I suppose, I should say this is the way the size will decrease. Now, tellurium, iodine, cesium, and barium are the ions in part C. So here's tellurium, which is taking on a -2 charge. It has, let's see, you'll notice that these are kind of selected so they're in the, oops, what did I choose wrong here? Cesium is what I didn't have. And barium. Of course, barium here is going to be smallest because it loses 2 electrons. Cesium is going to be next to the smallest because it only loses 1. So you'll notice that the more electrons that we've added makes tellurium the largest. And that's really what you need to understand to get number 40. Is the more electrons you add, and we're adding here to things that are kind of just lined up together on the periodic table. The more electrons we add, the larger the size.